This is part 2 of a review of basic integration techniques. If you haven't seen part 1 yet, either click the link in the upper right hand corner of your screen or find the link in the description. Number 8. Find the integral of x times the secant squared of x squared dx. Let's use U-substitution. We can probably solve this by letting u equal x squared because we see the x squared on the inside of the function. If u is equal to x squared, that means that u prime will equal 2x. So when we do the substitution, we have the integral of x times the secant squared of u. Instead of dx, we write du divided by u prime, which is 2x. And then we notice that we now have an x in the denominator and an x in the numerator. So these will cancel each other out. The 2 in the denominator will come out in the front of the integral as a 1/2. So now we have 1/2 times the integral of secant squared u du. We can use this derivative rule that we memorized first semester in order to integrate. So since the derivative of tangent is secant squared, that means the integral of secant squared is tangent. So we now have 1/2 of tangent u, and we have to put a plus c. Don't forget your constant of integration, very important. But remember that u is x squared. So for the final answer, we have 1/2 tangent x squared plus c. Number 9. Find the integral from 1 to 4 of the absolute value of x minus 2 minus 1 dx. To integrate an absolute value function, it is almost always easiest to graph the function and then integrate by finding the area between the x-axis and the curve. So before I do a proper graph, remember your transformations. First of all, the parent function y equals the absolute value of x is a V shape with a slope of 1 on the right and a slope of -1 on the left with a vertex at 0, 0. When you have a -2 on the inside of the function, that means that the graph will be shifted over 2 to the right. A -1 on the end means that the graph will be shifted 1 down. So again, this will be 2 to the right and 1 down. Here is the portion of the absolute value graph between 1 and 4, since those are the limits of integration. We need to find the area between the curve and the x-axis. So I see that we have a portion of the area that is below the x-axis and a portion that is above. Area below the x-axis is considered negative. So the first triangle has an area of -1. Area above the x-axis is positive. So the second triangle has an area of positive 1/2. If we put those together, the integral from 1 to 4 of this absolute value function is going to be -1 plus 1/2 or -0.5. So that's the answer for number 9. For number 10, let's try u substitution again. I see the x plus 2 inside of the parentheses. So let's try letting u be x plus 2. In that case, u prime will simply be 1. So let's do the substitution. We have the integral of x minus 3 over u to the 4th power. Instead of writing dx, we write du over u prime. But u prime is just 1, so I don't really need to write that. So I have a problem. The x's were not canceled out like we normally love to see. So what do? I'm stuck. Well, not exactly. Let's use this expression right here. Only let's solve for x. If we do that, we are subtracting 2 from both sides. and we get x is equal to u minus 2. We can get rid of the x now by replacing x with u minus 2. That gives us the integral of u minus 2 and then minus 3 over u to the 4th power du. Combining like terms, we have the integral of u minus 5 over u to the 4th power du. It's time to use the a plus b over c rule. If I have a plus b over c, I can split this up as two fractions by writing a over c plus b over c. So I can write the integral of u over u to the 4th power minus 5 over u to the 4th power. This simplifies, and we have the integral of 1 over u to the 3rd power minus 5 times 1 over u to the 4th power. This is the same as the integral of u to the negative 3 minus 5 times u to the negative 4 du. Using the power rule of integration, we will add 1 to this exponent, and we get u to the negative 2 power. Then we divide by the new exponent, so we have negative 1/2 in the front. Adding 1 to this exponent, we have u to the negative 3 power. Dividing by the new exponent, we will have positive 5 over 3 in the front. And let's go ahead and include the constant of integration. Don't forget the plus c. Putting x plus 2 back in for u, this is the final answer for number 10. Number 11, let's find the integral from pi over 6 to pi over 4 of cotangent 3x over sine 3x dx. We know how to integrate the 6 individual trig functions, but other than that, we only have a couple of memorized trig rules. From our derivative rules turned inside out, we know that the integral of secant squared u is equal to tangent u, because the derivative of tangent is secant squared. Similarly, we know that the integral of secant tangent is equal to secant, because the derivative of secant is secant tangent. And then we have the matching co-versions of each of these rules. Whenever I try to integrate a trig expression, one thing I like to do is see if I can get the expression to match one of these 4 rules. I notice that I have cotangent in the numerator, and looking at my 4 rules, I see a cotangent right here. So maybe I can manipulate this expression to look like this rule. I have memorized the following shortcut. Since the reciprocal of sine is cosecant, if you take a sine function and move it up to the numerator, it will become cosecant. So this expression is equivalent to this expression. If you are not comfortable with that, you can show this extra step. If I take the cotangent in the numerator and sort of put it off to the side, that will leave behind 1 over sine of 3x. This is clearly the reciprocal of sine, which can then be replaced with cosecant, and you're back to this. Now we can do a mental u substitution. The u is 3x, therefore u prime is 3. All that will happen is we will end up dividing by u prime. We will end up dividing by 3. Therefore, we will have a 1/3 out in the front of the integral. Other than that, we can go ahead and take the antiderivative of cosecant u cotangent u. And as I mentioned at the beginning of this problem, that integral is negative cosecant u plus c. So I'm going to put the negative in front of the 1/3. So then I will have the cosecant u, but I'm just going to put 3x because that's our u. So cosecant of u, and instead of putting plus c, I will apply the limits of integration from pi over 6 to pi over 4. This means we need to find the value at pi over 4 minus the value at pi over 6. So here is the value at pi over 4 minus the value at pi over 6. Of course, 3 pi over 6 simplifies down to pi over 2. So when you look at this, think cosecant of pi over 2. We know that cosecant is the reciprocal of sine. So what is the sine of 3 pi over 4? Whatever that is, we will just turn it upside down. Well, the sine of 3 pi over 4 is the same as the sine of pi over 4, except maybe it's negative. But the sine of pi over 4 is 1 over radical 2. You might have learned this as radical 2 over 2. That's the same thing, but I like to use 1 over radical 2. Will this be positive or negative? Well, 3 pi over 4 is in the second quadrant. Sine is a y value, so it's positive. So the sine of 3 pi over 4 is 1 over radical 2. Therefore, the cosecant will be the reciprocal of this. Turn it upside down and you just have radical 2. Now, what about the sine of 3 pi over 6? Well, the sine of pi over 2. Let's call it that. Pi over 2 is up here at the top of the unit circle. Sine is the y value, so that is going to be 1. And the reciprocal of 1 is still 1. So this is the final answer for number 11. Number 12. A particle moves along the y-axis. Its acceleration at time t is given by the equation a of t equals sine t plus 24t. At t equals 0, the particle is at rest and has a position y equals 4. Let y of t represent the particle's position at time t. Find an equation for y of t. We have this chain of calculus relating position, velocity, and acceleration. The derivative of position is a velocity function. The derivative of velocity is an acceleration function. You can go in the other direction by integrating. The integral of an acceleration function is velocity. The integral of a velocity function is position. In this case, they have given us an acceleration function, and they want us to find a position function. So we will need to integrate twice. Let's start by integrating both sides of this acceleration equation. The antiderivative of acceleration is velocity. So let's just go ahead and put v of t. Let's integrate the right side term by term. The integral of sine is negative cosine. And the antiderivative of 24t, well, let's see. We have to increase the exponent by 1, so that'll be t squared. Then we have to divide by the new exponent. 24 divided by 2 is 12. So we have plus 12. And don't forget the constant of integration. Very important. We can use this initial condition to find the value of c. At t equals 0, the particle is at rest. That means when t is 0, the velocity should be also 0. So let's plug in 0 for t. We get negative cosine 0 plus 12 times 0 squared plus c, and this should all equal 0. The cosine of 0 is 1. It's over here on the right-hand side of the unit circle. So this will be then negative 1. And this term is gone because that's just 0. So we have negative 1 plus c is equal to 0, which means that c is equal to 1. Let's substitute that in right here. So this is our complete velocity function. Let's integrate both sides of this equation to find an equation of position. The antiderivative of velocity is position, so we will put y of t. Now we integrate term by term on the right-hand side. The antiderivative of cosine is sine, and I'm just bringing down the negative. So we have negative sine t. Adding 1 to this exponent will give us t to the third power. Then we divide by the new exponent, so that gives us 4. So 4t cubed. the antiderivative of 1 is t. And don't forget the constant of integration. We've already used the letter c in this same problem, so we need to pick a different letter now. Let's call it d. We can use this initial condition to find the value of d. At t equals 0, the particle has position y equals 4. So if we plug in 0 for t, the answer should equal 4. So we have this, but the sign of 0 is 0, and 0 cubed and multiplied by 4, that's 0. We just straight up have a 0 right here. So all of this, the first three terms have a value of 0. So that just leaves us with d equals 4. Let's substitute that in right there. So this is the final answer for number 12. Number 13. Set up but do not evaluate a definite integral that could be used to find the area of the region bounded in the first quadrant by the x-axis, the y-axis, and the graph of y equals 8 minus x squared. Let's sketch a graph. Y equals 8 minus x squared is the same thing as y equals negative x squared plus 8. Comparing this to the parent function y equals x squared, which we know to be a parabola with vertex at the origin. Adding a plus 8 on the end shifts the vertex up 8. Having a negative in the front turns the parabola upside down. So this is an upside down parabola with its vertex at 0, 8. We are told that the graph is bounded in the first quadrant, so I'm going to erase that part of the parabola. The region bounded in the first quadrant by the x-axis, the y-axis, and the parabola is shown here in yellow. We need to set up a definite integral that would represent this area. To find the definite integral, we need to know this intersection point. We need to know this x-intercept. We can find that by plugging in 0 for y. In other words, if we set this function equal to 0 and solve, that's how you find an x-intercept. Adding x squared to both sides, we have x squared is equal to 8. Taking the square root of both sides, we have x is equal to plus or minus the square root of 8. I said plus or minus. Why didn't I write down plus or minus? Well, we're in the first quadrant. Everything's positive, so it's just radical 8. So that is the x-intercept right here. So this spot is at an x value of radical 8. We can set up the integral now. The limits of integration will be the width of this interval from 0 to radical 8. So we will say the integral from 0 to radical 8. And we're talking about the area under this curve. So we can just go ahead and put in the function 8 minus x squared. And don't forget your dx on the end. And that's it. That's the answer to number 13. Last one, number 14. Let u equal x squared plus 1. Fill in each box with a number to make this a true statement. When we do U-substitution on a definite integral, one strategy that we use is to take away the limits of integration, and then we just perform the integration like an indefinite integral, and then after the U-substitution is over and we have the x's back, then we suddenly bring back the limits of integration and finish the problem. But another way to do the problem is to actually change the existing limits of integration to new limits of integration that will be written in terms of u instead of x, which is what we have now. So that's what we're going to do on this problem. U is x squared plus 1. That means that u prime is going to equal 2x. So when we do the substitution, we're going to have x times u to the 4th power, and then instead of dx, we will write du over u prime, which is 2x. But then we notice that we have the x in the numerator and this x in the denominator, which cancel each other out. So those are going to be gone, and we will be left with this 2 in the denominator. We can bring that out in the front as a 1/2. But that's what this box is for. So I'm going to have a 1/2 right here. Now let's talk about the limits of integration. This is an x value, and so is this. On the other hand, this is a value of u, and so is this. So, how do I turn an x value into a u value? Well, we're going to use this equation right here. U is equal to x squared plus 1. So this u right here is going to equal this x squared plus 1. So it's going to be 4 squared plus 1. That's 16 plus 1, which is 17. Okay, so I'm going to put that here as well. And then similarly down here, it's going to be this x squared plus 1. So this is going to be -2 squared plus 1. That's 4 plus 1, which is 5. So we have this. So this is really the end of this problem, because all they were asking us to do is fill in the boxes. But just for fun, I want to keep going and show you how you would finish a problem like this once you have changed the limits of integration to now match your u. The cool thing is that now that we have changed the limits of integration from x's over to u's, we will not have to substitute x squared plus 1 back into the equation. We can just finish it out with the u. So the antiderivative of u to the 4th power, I'm going to add 1 to the exponent, so I have u to the 5th power. And then I will divide by my new power. So I'm dividing by 5. I have this 1/2, so if I divide by 5, this is going to be 1/10. So now I have 1/10 u to the 5th power, and here I am applying my brand new limits of integration from 5 to 17. So this means that we will find the value at 17 minus the value at 5. So if they had asked us to integrate, this would be the answer. But we didn't really need to do that. We were done as soon as we filled in the boxes.